Okay, I think we should get started. So in terms of time, Benedikt, we're aiming for 40 minutes. And again, this is recorded, as it says up top, and it will go on YouTube. So let's get started. Thank you, Benedikt, for being here. And please go ahead.
Okay, yeah, thanks, Ale, and thanks everyone for coming. I'll talk about proofs for inner pairing products and applications. And this is work that we actually started while doing the Simon's workshop. So this is a direct result of this, and it's joint work with Mary, Pratyush, Nirvan, and Sai. And we just updated the paper online. So even if you have had a look at it, I encourage you to download the new version, which has a lot more evaluation, and I think it's better written, and you should definitely go check it out. So what is an inner pairing product? What are we constructing? Well, we're constructing proofs, efficient algebraic proofs for these bilinear languages. So very generally, or at a very high level, we're going to prove statements like there exists vectors A and B of group elements in bilinear groups, such that some public value T is the product of the pairings of each of the individual elements. And things that we achieve are that we have a very efficient prover. It uses n pairings roughly, or on the order of n pairings. And the efficient prover will actually be a big highlight, because a lot of the things that we achieve, you could previously only achieve with recursive composition. And there, this recursive composition of SNARKs requires very expensive NP reductions. So there the cost would be maybe on the, you have the NP reduction has a blow up maybe of a factor of 1,000 or something along those lines. And you can see that in our evaluations. And then we also have very succinct proofs. So our proofs are a logarithmic number of elements. And we want the verifier, we achieve that the verifier is also going to be efficient. And we use many different protocols, but they're all the instantiations of one generalized protocol. And we are one generalized argument system, which we then optimize for different implementations. And one of our contributions is this generalized argument system, for which we can present one security proof, and then you can instantiate it in many different ways and immediately get secure protocols out of it with different properties. So I first want to talk about a couple of the applications that we have. So one of the first and main applications that our protocol has is a polynomial commitment scheme. So in a polynomial commitment scheme, you commit to a degree D polynomial using a short commitment. And then the prover can convince the verifier that the polynomial evaluated at a point Z has some particular value, and that the degree of the polynomial is bounded. And these polynomial commitments have received a lot of excitement in the last, I would say, 1 or 2 years. And mainly this is because you can actually build full-fledged SNARKs for NP using these polynomial commitments. And for the most part, the efficiency properties of the polynomial commitment dictate the efficiency properties of the SNARK. So if you have a very efficient polynomial commitment, or whatever cryptographic properties or whatever efficiency properties your polynomial commitment has, these are almost directly going to be the efficiency properties of your SNARK for NP. And also you can use polynomial commitments to build accumulators and vector commitments. And so they're a very useful tool. So the particular polynomial commitment that we build has a couple really nice properties. Main in that, so here's a comparison to the probably most widely used polynomial commitment scheme, which is called the KZG polynomial commitment scheme. And the key areas in which our commitment scheme shines is that it has a much smaller reference string. So the reference string is only asymptotically only square root in the degree of the polynomial. And the evaluation prover also only uses square root of the cryptographic operations. So of course, the evaluation prover has to evaluate the polynomial, but in addition to that, it only performs square root of the kind of cryptographic operations. And you can see this translate in our implementation. So at a very large, for a very large degree, 2 to the 26 polynomial, I think this is like 200, well, now I'm getting my exponent. You can see that the CRS size is only 4 megabytes versus in a KZG commitment scheme, the CRS size is would be 3.2 gigabytes, and the evaluation prover takes 15 seconds versus 60 minutes. And especially the CRS size is something that is actually very much a constraint in practice. We've talked to, for example, Filecoin, and they want to create these proofs for gigantic statements, and they have the problem that if you have a very large CRS, then this has to get sent around the network to all the different provers who want to use it. So this is actually a practical constraint. And what are the trade-offs? Well, the trade-offs are that our proofs are a little bit, or they are larger. They are, the KZG proofs are constant size, only 380 bytes. And for us, this is on the order of less than, say, 4 kilobytes. And the verifier time is also a little bit larger, so 46 milliseconds versus 5 milliseconds. But there are certainly applications where, you know, the verifier time and the proof size are not the bottlenecks anymore, but the prover and the CRS size become the bottlenecks. And then this polynomial commitment scheme might be a good application for that. The second application is related to something called Rollup. So Rollup is a concept that is now also widely used in the blockchain space. So traditionally, you have, if you have a bunch of blockchain users who all have transactions, well, then they post all of this transaction on the blockchain, and every single miner, every single verifier in the blockchain consensus system has to verify all of the transactions. And the idea of Rollup is to introduce a so-called Rollup server, which collects all of the transactions and then creates, verifies all of them and creates a short proof, short snark, that all the transactions are valid. And then the Rollup server sends a summary of the transactions and the short proof to the miners, and the miners just verify this proof. And it turns out that verifying the proof is significantly more efficient than verifying, say, tens of thousands of transactions. So this is an efficiency gain that is achieved here using this Rollup. But sometimes you want to have also Rollup with privacy. So you want to have transactions that themselves reveal no information or have less information about how much money a person is transacting to another person. So the way to achieve privacy, I won't go into any details of how this works, but is to use also ZK snarks at the transaction level. So every single transaction now has a ZK snark asserting that whatever state update this, or whatever local state update the transaction does, is in fact valid with respect to, say, some commitment to the state. And if these commitments are hiding, then the snark, then there's no privacy leak. The details of the transactions don't have to get revealed. But now the problem is that the Rollup server has to actually provide a proof that it still has to verify the transactions and provide a proof that it did this correctly. But the problem is now that verifying transactions actually involves checking snarks themselves. So what we would need is a way, sort of a classical way to achieve this is by using recursive snarks. So the Rollup server would produce a snark that asserts that all of the transaction snarks are in fact valid. And what we want is kind of a way to, or in more general, what we would like to do is have a way that we can just aggregate all of the transaction snarks into a single small snark. And we, in fact, achieve that. So we build a protocol for aggregating snarks that does not use recursion. So you can combine many snarks into a short proof. And in particular, this isn't a generic protocol that works for any snark. This works in particular for pairing-based snarks like Groth16. And previously, as I said, this was only known from one-level recursion. And the key benefit here is that our aggregation protocol is completely algebraic. So it doesn't rely, again, it doesn't rely on these very expensive NP reductions. And you can see this in the fact that, say I want to aggregate 64 snarks, then our approach takes, the aggregation procedure takes 1.1 seconds, versus with one-level recursion, it requires 18 minutes and 256 gigabytes of memory. And the large memory comes from having to compute a very large FFT here. So it seems somewhat inherent that, that you need that much memory. And after that, after 64, so this is a 900x speedup. And after 64 proofs, the one-level recursion approach unfortunately runs out of, our machine ran out of memory. We didn't have a big enough machine, but we ran our aggregation protocol further, and we can see that in less time, so in 12 minutes, we can aggregate 65,000 proofs. So 1,000 times more proofs in less time. So yeah, so this shows you the very concrete efficiency gains from using the protocol. We further extended the protocol to enable low memory proofs, low memory snarks for machines. So say you have a machine that takes T steps of complexity C, and you wanted to prove that the machine evaluated correctly. It did the computation of T steps correctly. And if you naively do a monolithic proof, then this takes O tilde of C times T space. So it takes quite a lot of space. And our approach is that you simply create T snarks, each asserting a single transition. And then you use the inner pairing product to aggregate all of these snarks. And we can take advantage of the structure of this computation, so that the input of one computation, or the output of one computation step, is the input of the next computation step, such that the verifier is going to be logarithmic in the number of steps. So the verifier is succinct. This is very efficient. And the space that is used is only C plus T. So it's O of T because you need to store all the intermediate proofs, one for each step, but it's not the product of C times T, because you don't need to keep the entire internal state of the machine around, because at every step you compress it using an individual snark. And with recursive snark, you can actually get something even better. So you can get O of C space, but recursive snarks, as we've seen in the previous application, they have the downside of often having very large constants. So it's an application where we get something not quite as good asymptotically as the best known solution, but something that is likely to be much more practical or has much better constants. And as the final application, we can, the final application is related to BLS signature aggregation. So just to quickly recall, if I have a signature aggregation, means that I have n signatures from n different public keys on n different messages. And there's a public aggregation protocol, which anyone can run, to create a single short signature. And verifying the single short signature convinces the verifier that all of the that the users I through N signed the statements M1 through Mn. But the problem with BLS signature aggregation is that the verification still requires one pairing per aggregated signature. So you still need to do N expensive pairings, or so they're not extremely expensive, but they're somewhat expensive, and we would like to reduce this the cost of these N pairings. And this is exactly our fourth application. We have a protocol for outsourcing pairings. So it's a protocol where, say you want to do some verifier has to do N pairings, it can outsource that computation very efficiently to a prover. And then the verifier still does linear work, but it only does 2N exponentiations. And exponentiations are generally cheaper, and you can use multi-exponentiation. It's really a multi-exponentiation of size 2N. And you can outsource this using a log n size proof. And concretely, this gives you about an 8x speed up at n equals 2 to the 20. And one nice property is that at least the interactive version of this protocol is actually a statistically sound proof. So how do we achieve all of this? Well, the main protocol that we base our inner pairing product on is the inner product argument from Boodle et al. That is also used in, or this particular variant is from bulletproofs. And in the inner product argument, you have a commitment to two vectors and a scalar. So this commitment, the commitment function here is denoted by H. And in particular, it's a Patterson commitment. So you commit to so A and B are elements in a prime field, and you commit to them using this Patterson commitment and the inner product of A and B. And bulletproofs at a very high level works by reducing a statement of size n about vectors A and B, so to a statement of size n over 2. So you have a one-round interactive interaction with a verifier in which the prover sends two commitments and the verifier sends one challenge. And after that, you've reduced the statement to a state about the vectors A prime and B prime. And these vectors are now of half the size. And you can run the protocol for a logarithmic number of rounds. And in the end, you have to do one evaluation of H on a constant statement. And the total communication is only 2 log n commitments. So 2 commitments per round and log n round. And the verify work is linear still in the original statement, but all of the work, it turns out, and this will become important later, is in computing the final commitment key. So what we looked at is whether we can use the same structure of argument for other protocols. So not just for this kind of inner product argument where you commit to field element vectors, but what are the properties of H here that are important to apply this, or how can we apply the same structure of argument to other, to get other protocols? And the key insight is that H, so we wanted to abstract the properties of H used in the inner product argument. And one key insight is that H is homomorphic in both the commitment key and in the messages. So we can say that H is a doubly homomorphic function. So to see this, we have G to the A is times G to the B is the same as G to the A plus B. I'm using this vectorized notation here. And we can see that, so G and H are the commitment keys and A and B are the messages. So the first equation here is that it's linear in the linear in the message space, and it's also linear in the commitment key space. So G and H are the commitment keys. And it turns out that if we can use a similar protocol for other doubly homomorphic commitments. And in particular, we call these inner product commitments. So for an inner product commitment H, we have 3 prime order groups, M1, M2, M3, and we have some bilinear map between M1, M2, and M3. So in the inner product argument, M1 and M2 are both just a prime field, and the bilinear map is just multiplication, or M1, M2, and M3 are actually the prime field, and the bilinear map is just the multiplication in that field. But it turns out that we can generalize the protocol to use more general bilinear maps. It doesn't actually, we don't really need that many properties, or the only property that we need is that the map is bilinear. And we can also apply this to more general prime order groups. And what our commitment H provides, it's binding and C. So A and B are size M vectors, and C is a scalar. And then the protocol that we provide, this generalization or this generalized inner product argument, GIPA, is a proof that C is the inner product between A and B. And GIPA has exactly the same, or it uses exactly as the argument, just using this generalization and this abstraction of H. And we prove that, or we first prove that GIPA is secure by saying that the interactive variant of GIPA is a proof of knowledge for this relation here that I just said, so that you have a commitment to A, B, and a scalar, and that the scalar is the inner product between A and B. And we prove that it's a proof of knowledge for this relation or extracting a break of the binding property of H. And because if we assume that H is a binding commitment, well, then we can prove that GIPA is an argument of knowledge for the relation or GIPA that is parameterized by H. But in practice, most of the applications actually require non-interactive, and so this protocol, the security proof it's very similar to the security proof for the inner product argument, but one of the nice properties is that it really generalizes about for all of these protocols, and we can now just come up with a new hash function with a new inner product commitment H. And as long as we can show that it's binding, or we can assume that it's binding, well, then we know that, and we immediately have a protocol for it, a GIPA variant for it, and we immediately know that it's secure by theorem 1. But one problem is that most applications of our protocols, and in general also for bulletproofs and other protocols based on the inner product argument, require non-interactive arguments. And the way that we get a non-interactive argument is we apply the Fiat-Shamir transform to, so GIPA is a public coin protocol, so we can apply the Fiat-Shamir transform which gives us a non-interactive protocol. The one problem with that is that if we naively apply the Fiat-Shamir transform to a logarithmic round protocol like GIPA, this gives us a super polynomial extractor. So the extractor then runs in time polylambda to the log lambda. And so this is, I mean, this is at least, this is not what we would like. We would like to have a polynomial time extractor. And so we at least somewhat alleviate these concerns by showing that if we treat H as an algebraic commitment, so we look at H in an algebraic group model, or in kind of we call it an algebraic commitment model, then the Fiat-Shamir transform of GIPA is a non-interactive argument of knowledge. So in the random, it's a non-interactive argument of knowledge in the random oracle model, given that H is a binding commitment. And in the proof, extracting, because we're in this algebraic commitment model, extracting A, B, and C is trivial. This is immediately given to us by this idealized model. But then the difficulty comes in showing that C is in fact the inner product between A and B. And we rely on a zero finding game that which bounds the probability that if an adversary comes up with a polynomial and then commits to that polynomial, and we generate a challenge from the commitment of the polynomial, then it's something here was missing. Then it's unlikely that the polynomial at this random point, or this point generated by the random oracle, is zero unless the polynomial itself is zero. So we have we from this prior paper, we have a very concrete bound on what that probability is. And using this bound, we can actually prove our theorem too. Or we apply this multiple times at every round. So yeah, so the nice thing of theorem 2 is that it applies to all GIPA protocols. So for example, it also applies to bullet proofs and other instantiations like LMR 19 and other instantiations that have this similar structure, and that were previously only proven secure in their interactive variants. So now how can we instantiate GIPA? Well, we can use the Patterson commitment, which gives us the bulletproof variant. We can also instantiate it using the AFGHO commitment, which is a commitment to group elements and uses bilinear groups. So this gives us kind of this is what we're mostly using through the paper. Gives us the inner pairing product. And this variant has also been used previously by LMR 19 to also produce proofs on group elements. And the most direct instantiation of it has a communication of 6 log n target group elements. And it still has linear verification time, and we'll get to getting around the last fact in a second. And interestingly, it sometimes even makes sense to commit to use the identity commitment. So the commitment to A and B would then just literally be the vectors A and B and the inner product. And this can be useful, or using GIPA in that way can be useful if computing the inner product or evaluating the bilinear map is expensive itself. And this is exactly what this protocol is exactly what we're using for outsourcing pairings. So now we want to, so we have this nice protocol now for these pairing arguments. And there's been even prior work on exactly that by LMR 19. But this protocol still has this linear verification time. And it turns out that the expensive cost for the verifier in GIPA is computing the final commitment key. So in every round, you have to update your commitment key. And in the end, you have a final commitment key. And it turns out that, so if we look at, let L x1 through x log n be the challenges that are generated in each round. So x1 is the first round challenge and x log n is the last one's challenge. And G is the original commitment key. So it's a vector of size n. Then the polynomial P of y is, which has this form and is a degree n polynomial. It turns out that the final commitment key, G final, is exactly a Patterson commitment to the coefficients of P. And this is an observation that was done by Bowie, Griggs, and Hopwood in the Halo paper. And the interesting thing is that if you look closely at this polynomial P of y, so it's a degree n polynomial, and if you expand it, it has n different coefficients. But so computing g to the p is actually takes time O of n, but P of y can be efficiently evaluated. So evaluating it at any point z only takes time O of log n. So this can be evaluated in time O of log. Okay, writing with a mouse pad is not very efficient, but so we are going to take advantage of exactly this fact. So the idea that we have is we want to outsource the computation of G final to the prover, right? And here up here, we have exactly the structure of G final. And what we're going to do is we're going to use a structured reference string. So for a secret value S, the reference string is G to the monomials of S in a bilinear group. And then it turns out that G final is a KZG polynomial commitment to this polynomial P of y. So if you're not familiar with KZG, you have to trust me on this, but you can see that it's G final is equal to P evaluated at S. And this is exactly the structure of the KZG polynomial commitment scheme. And then the protocol is going to be that the prover sends G final, or its claim of G final, to the verifier. The verifier will sample a random challenge Z, and the prover will convince the verifier that the polynomial inside G final evaluated at Z is exactly equal to P of Z. And it's important that the verifier can themselves compute P of Z. Right? This is a very, this computation itself is efficient. So the prover then provides this KZG proof to show that G final has exactly the right structure. And given that, the verifier can accept G final and use it in the TIPP protocol. So there's some important details, of course, missing here, and you can see the paper for to find them. So the summary is that TIPP is secure. Security is based on the security of GIPA and instantiated with the correct inner product commitment and the security of KZG. And it uses this structured updatable reference string. So it is a trusted setup, but one that is updatable. And the important property is now that the verifier doesn't have to do linear work anymore, because the one expensive computation step we've outsourced to the prover. So the verifier only performs 6 pairings and 6 log n exponentiation in GT. And we use multiple variants of TIPP. For example, sometimes you don't want to commit to 2 vectors of group elements, but just 1 vector of group elements, and have an inner product with, say, a public vector of values, and so on and so forth. And for that, we use, we have a 2 log n. So in some of these variants, we have even shorter proofs. But the nice thing, again, using GIPA, it's very simple to instantiate all of these different protocols, or all of these different variants, and immediately have security proofs for them. So now, and this is, well, yeah, so now we can use TIPP to construct a polynomial commitment. So say we have a bivariate polynomial commitment. So P of x comma y is degree n in x and degree m in y. And it turns out that if you have a univariate polynomial, you can easily transform it into a bivariate polynomial where n and m are about square root of b. And we're using the Groth 11 two-tiered commitment scheme, which writes it basically, the first step is to write our so Groth 11's commitment scheme is a commitment scheme for matrices, and we can write our coefficients as a matrix A. So this is an m by n matrix A, and each entry is one of the coefficients of the polynomial P. And then we commit to each row using a Patterson commitment, and then commit to the row commitments, right? So these are now group elements using the AFGHO commitment. So this is using a pairing product. And note that the final commitment to this matrix is still doubly homomorphic. And if we want to evaluate the polynomial at a point x comma y, well, then this is simply the a vector matrix vector product using the vectors x, which is the monomials of the challenge x, of the evaluation point x, and the vector y, which consists of the monomials of the evaluation point y. So if we want to construct an evaluation proof, we now have to construct a proof for this vector matrix vector product. So for this quadratic form. And the untrusted variant is simply going to use an inner pairing product. So this is GIPA instantiated with AFGO to compute x times a. And then we have a prime, which is the result. And that is, then we can simply use bullet proofs or GIPA with instantiated with the Patterson commitment to compute a prime times y. And in the end, this protocol has a logarithmic communication. But the interesting thing is that the prover and verifier complexity is not linear in m times n, but it's linear in m plus n. And same with the reference string size. But because we set m to be roughly equal to the square root of d and n the same, then both the prover and the verifier complexity are just on the order of square root of d, and the size of the reference string as well. So can we do better than this? Well, yeah, with our trusted setup protocol, we can use a structured reference string, and then in the first step, we're going to use our TIPP protocol. So this is the trusted protocol that I just presented to compute a prime. And then in the second protocol, we note that a prime is already a KZG commitment to the univariate polynomial p of x comma y. And we can simply open this KZG commitment at the point little y. And now this protocol has, again, still has even less communication. But now it has, the verifier complexity has been reduced to log n, and which is O of log d. But the important thing is, you might wonder, okay, this is a trusted variant, and with a trusted setup under the same assumptions, we already have the KZG polynomial commitment, which has even less, it has constant verifier complexity. But the key benefits here are that the prover complexity is still just m plus n, and the verifier and the reference string, the structured updatable CRS, is also just m plus n, which in the end gives us a complexity of square root of d for both of these things. So this is the key benefit compared to the KZG polynomial commitment. And there's been really exciting, very recent work by Lee called Dory, which builds upon our polynomial commitment. So the commitment has the same structure, and it also uses a different variant of the inner product argument. It doesn't actually fall, it's a very, very cute protocol. It doesn't fall into our generalization. But the nice properties are that it has similar, the same asymptotics, but it does not rely on a trusted setup. So it also has a logarithmic verifier, but it does not rely on a trusted setup. It has slightly worse, or it has, well, it has worse constants than our protocol. But again, you know, it's a really, really nice nice result. So we've implemented and well, and when I say we, I mean not me personally, but Nuran and Rajesh, who've done an amazing work on this. They've implemented TIPP in the ArcWorks library family. We call the library, it's open source and online, and you can go play around with it. We call it RIP. And we compared it to the KZG polynomial commitment. And you can see that especially on the CRS size and the setup time, here, this is really where our protocol starts to shine. So I think, what did I say earlier? It's for this point here, degree 2 to the 26, or well, this is the last point actually. You have something like 3 gigabytes versus only a few megabytes. And also the opening time or evaluation time grows only as square root of D, and this shows up in the concrete numbers. And the verification time and the opening size is larger, but it remains sort of reasonable for all of the values that we've tested. I very quickly want to also talk about the SNARK aggregation section. I think, well, so this was the
try to wrap up in a few minutes.
Okay, I'll do this in 1 minute. So I'll actually skip over the protocol. So, but what we're able to do is we're able to build a protocol using, again, these inner products, or our TIPP protocol, to aggregate n gross 16 SNARKs. And you can, so the key benefits of this protocol are that the aggregator only does 10 n pairings. So the aggregator does not have to rely on expensive NP reductions in order to do the SNARK aggregation. And here, this is the one slide I wanted to show. Is that here we compare our approach with Zexi, which was is a one-level recursion protocol. And you can see that at 64 proofs, I think we're, so the key thing to look up is here is the aggregation time. So at 64 proofs, I think this is a gap of, this is 900x speed up. And after that, the Zexi protocol runs out of memory, and we can, you know, continue our protocol without sort of any of the issues. So it's about, yeah, factor 900 to 1,000 times faster, and can be run on about 1,000 times greater instances. So yeah, thank you very much, and you can find the paper online.
Thank you, Benedikt. Right on time. Perfect. Thank you so much. Are there questions for Benedikt?
I do have one.
Go ahead.
Hello, it's Patrick here. Benedikt, you mentioned in your talk that applying PHME transform to basically these recursive arguments will result in super polynomial extractors. And I was wondering, to which extractor do you refer to? Is it the one from the paper in 2016 by Boutel et al., or is it the corrected version that appeared a bit later by Del Pino, Zeiler, and Yubashevsky?
So my my understanding is, so this is the kind of the Fulcor way to transform or to show that a Fiat-Shamir protocol is secure in the random oracle, is that basically if you're well for either of these extractors, you build a for every round where you need to rewind the prover. So the way that the extractor works, and I'm not, and these are all the interactive. So I think there's been multiple security proofs, but all the interactive security proofs that I've seen, the interactive extraction, it relies on rewinding. So you have to rewind the prover to for every round to get him to respond on different challenges, and this is if I do the Fiat-Shamir transform and I have an adversary that is allowed to do T random oracle queries. I think the only way that we really know how to do this rewinding is in every round you pay a factor of T and then it multiplies across the rounds. So this is where that you get the T log T to the number of rounds. Factor, and this turns out to be super polynomial in the security parameter. So I don't know the exact answer to your question, but I think it applies to. So as far as I know, I think we just don't know. I mean, maybe there's a way to prove. I mean, I think this is a great open question, but I haven't seen sort of a way to do the non-interactive proof in a non-idealized model.
Okay, so maybe I can be a bit more precise here. So the way it's proven in the 2016 paper is that, so like you mentioned, at each recursion step, you necessarily need to get like 5 different distinct, pairwise distinct challenge values, I guess, right, at each recursion step. So you end up with a tree. And the question is, how do you build this tree? And in the 16 version, there was an issue because basically the extractor would fix a value at one step of the protocol, continue, and then and then it would end up, let's say, in the middle of the tree, and then we'll have to generate different values. But he wasn't sure whether the path to the tree up till there was one that would lead to actually high probability or not. So basically the correction was to, from the beginning of the tree and before appending a new node, try to estimate whether the node that we just picked was a good one. And by doing so, I mean, one can prove that the extractor there runs in polynomial time. But then, of course, this is in the interactive version. What you're mentioning is that, okay, if I do Fiat-Shamir, then there would be a nested rewinding. That's what you're saying. But in a sense, I have a feeling that this corrected version already sort of takes care of this nesting. I'm not entirely sure
so
why.
It would be, so, right. So you're right. I mean, it's all about the forking lemma, right? Like where it's you know, we basically need to get a log round forking lemma in the for the non-interactive variant, and yeah, I would be very interested. I don't actually know the answer, but maybe it takes care of that, but I haven't seen that. And
I'm not sure. It's just my intuition that it should, but okay. But we can have this exchange via emails afterwards if you want.
Yeah, I would be very interested in that.
Yeah. So basically, yeah, this correction, there was a corrected version afterwards, and perhaps you can have a look at that. And also, there is a paper at TCC, I think 2019 or 20, which tries to analyze the version of the 2016 paper.
Yeah, so I think Stefano, this is the paper by Stefano Tesaro. So this deals with the fact that the 2016 forking lemma is, or it mainly deals, I think, with the fact that it's an expected time analysis, so that the extractor succeeds in producing this tree of transcript in expected polynomial time, but not in, we don't really have a worst case bound. And Stefano's paper, I think, looks very carefully at that and gives concrete security bounds. But I still don't think this solves the non-interactive problem.
Is for the 16 version. Okay. Sure.
Yeah, I would be. I mean, I would be really interested in to see it, but yeah.
Okay, thank you.
So there is another paper from University of Washington, right? The one by Astrojit and Stefano that does look at the non-interactive version.
So I think they do something at least. I mean, I think they do something similar to us. I think just a lot more general and looking at more general. I think the play between Fiat-Shamir and the algebraic group model. While we focus on, kind of our one protocol family. So I think that is, that is, I think the very similar ideas there.
More questions for Benedikt? Okay, wonderful. So if there aren't more questions, then thanks again, Benedikt, for giving a great talk. And so we have another morning talk in 5 minutes. So I suggest people may take a break, walk around a bit, and we're going to resume in a little over 5 minutes with Jonathan's talk.